Good morning or afternoon or evening, wherever you are. My name is Anu. I'm a chemical engineering graduate from Georgia Tech. And today we're talking about TXY diagrams, which is one of the early diagrams that you actually learn in chemical engineering. It's extremely useful, especially for your thermodynamics courses, as well as when you get into later into separations. So in this video, we'll talk about what a TXY diagram is, why you should actually care about this in the first place, how to read one, of course, and how to actually look at it. And then finally, how to use it so that you can actually solve engineering problems, which is the most important thing at the end of the day, right? So let's get into it. The first thing I want to do is give you a really a conceptual understanding of why TXY diagrams and what it actually is going to show us. So I want you to first start and imagine that we just have a container that has pure 100% water in it. Is at 1 atmosphere. And let's say we start at, what's a good temperature to start at? Let's say we start at 20 degrees Celsius, room temperature water. Okay? So at this temperature, water is basically 100% liquid. There is a small amount of vapor in the air. This is the vapor pressure, right? And it's definitely less than 1 atm. That's why we were in the liquid phase. So there is a little bit of vapor, just like there's a little bit of water. But it's mostly water. It's mostly liquid. And now we're going to heat this up. We're going to increase our temperature. So increase T. So as we increase T, that's also going to increase the vapor pressure of our water. And eventually, we reach a point at 100 degrees Celsius where the vapor pressure is equal to the atmospheric pressure, 1 atm. In which case, everything is a vapor. Okay, so this is for a single system. So we just have liquid, and then at 100 degrees Celsius, it becomes vapor. And even in the between point, when we have both water, liquid water, and vapor, we understand basically intuitively that both the vapor and the liquid are 100% water. They have the same composition. Now, this is not always the case when we have, say, a mixture. So suppose we have two species. We'll say A and B. And now we have a container full of liquid. And we have some mixture of A and B. And this can be two different things, right? Let's say this is like two hydrocarbons, for example, ethanol and methanol, right? These are pretty compatible, but they have different boiling points, different vapor or different different boiling points, and thus different vapor pressures at different temperatures. Or perhaps there's something a little bit more incompatible. We'll get into those. One famous one that we talk about in chemical engineering a lot is water and ethanol. So we'll talk about how to actually deal with water ethanol mixtures. But essentially, same thing, 20 degrees Celsius, 1 atm. Basically liquid. There's probably some little bit of vapor, but there's not much. Then you get to some intermediate. Let's just say we're around 40 degrees Celsius. And now we have non-negligible vapor pressure at this point. So some of the species in the liquid have become vapor. So they've gone into the vapor phase. But remember, A and B have they have different boiling points. They have different temperatures. So there's going to be a different amount of B than A that's going to go into the vapor phase. So you might have an A-rich liquid phase, for example, and a B-rich vapor phase. Then, of course, you heat it up even more. you get to 60 degrees, and now all of a sudden you have 100% vapor again. And so really what we're curious about is this middle portion right here, where we have this liquid and vapor phase coexisting at the same time. And the question is, what is the composition of the vapor phase and the liquid phase? You can probably see how this might be useful. Suppose we just have a reaction, comes in A, and then this is A to B, and out comes A and B. And we want to separate them. Well, we might use a simple flash unit, which is what it's called, that gets it to a specific temperature and pressure, and that gives you a vapor phase and a liquid phase. And then we can use the fact that this property of A and B having different boiling points to get a vapor-rich phase that has mostly B and a liquid-rich phase that is mostly A. In this way, we can actually separate out the two materials. So hopefully this gives you an intuitive idea of why we care about this. Now let's show what this looks diagrammatically. So what a TXY diagram looks like is for a given pressure, say 1 atm, we plot temperature on the y-axis and the liquid fraction of one of the species, so XA. So obviously liquid fraction goes from 0, 1.2 all the way to 1. And then temperature, we typically don't go all the way from 0. We go from some temperature that makes sense, some range. So maybe we start at, I don't know, 40 degrees Celsius, then 45, and then so forth, all the way to 100. And so there's really two temperatures we care about. Call this TB2 and, sorry. This is the boiling temperature of species B, and this is the boiling temperature of species A. So B has a higher boiling temperature than A. Lines like this. So what we basically want to do is show the division between vapor and liquid. And so imagine we have a species that is pure B, right? So that means XA equals 0. Well, it's going to be liquid, liquid, liquid until we reach the boiling point of B, and then it's going to turn into vapor. And as we increase the portion of A, the overall boiling temperature is going to decrease, such that once we reach 1, it becomes 100% A, means that we're going to switch to vapor once we've hit TBA. Draw the blue line very similarly. And so basically the way you read this is for a given composition, you can tell whether you are in the liquid, in the vapor, or have a two-phase situation going on. So again, if I have 100% A, this point is a liquid. This point is a liquid. But as soon as I cross the boiling temperature of A, now I have a vapor. Now I have a vapor. Same thing with B, but it's in between that we really, really care about. So, for example, suppose we're at 0.5. So this point is a liquid. This point is a vapor. But this point right in the middle is not either one of them. It's both of them, essentially. We have both a liquid phase and a vapor phase. So let's call this, it's we'll also call this T1. So at T1, we have now a liquid phase and a vapor phase. And the question is, what is the composition? Well, we can go across this line and actually look at where those points intersect. So we can see that the liquid phase, in this case, we can say that's around 0.15. So we can say that in the liquid phase, we have xa equal to 0.15, xb equal to 1 minus that, or 0.85. So the liquid phase is B rich. In the vapor phase, we go down and okay, maybe we say that's 0.75. So now we have XA, or not XA, sorry, X. We typically use X for liquid and Y for vapor. Oh, and there we have it. We have the compositions just from the diagram of what the liquid and the vapor streams are actually going to be. So in essence, this TXY diagram allows you to actually see how those are set apart. Now, how do we actually get all these two lines, right? And there's a couple ways, and you'll learn this in your intro course. I'm not going to go over them super in detail in this video. I'll go over them maybe in a separate video. But you have some other ones. Perhaps they're tabulated, so maybe you can go to Perry's or NIST. Usually very common mixtures like ethanol water. They're very well researched, so they have a lot of data on that. If you don't have that, you can get parameters for, say, the Antoine's equations. And so on and so forth. There's other things that we can do here. And basically, all we're trying to do here is calculate what is the vapor pressure of A and B at any given temperature. So at temperature X and obviously this pressure, what is the vapor pressure? And we can do that usually using Anton's equations, or if you have the tabulated values. Obviously, tabulated is better in this case. All right, the one last point I'll make here is that sometimes, typically what happens is the boiling points will meet at one point, but they can actually intersect each other at a different point beforehand. So I'll give you an example of that here. So suppose I have T and X, XA, sorry. And this is T boiling B, T boiling A. This is 1. And so what you can actually have happen is I'll call this XA, A for azeotrope. What you might have happen here. So what you might have happen here is that they might meet up in the middle. So this is called an azeotrope. So at this composition, essentially there is no separation into a liquid phase and a vapor phase. You go straight from liquid to vapor. So you have liquid, liquid, and then suddenly vapor, vapor, vapor. And this is very common in things that are very incompatible, such as like water and ethanol. So you'll see this very commonly where water and ethanol will combine, and you get to this point, this azeotrope point, and you can no longer separate them because you can't have a vapor phase and a liquid phase anymore. You either have all vapor or all liquid. That's it. And so you get stuck in this point here. Okay, I'm actually running low on time on the Zoom meeting here. So I will do the worked examples in another video. But what I will do is show you something pretty cool that you can actually do with TXY diagrams. And this is actually a recent thing that Claude came out with that I think will be interesting to you. Basically, Claude now allows you to Claude now allows you to essentially create interactive diagrams here. So I said create an interactive TXY diagram, and then I also gave it some tabulated values that I found from the internet. So you get this sort of diagram here. And so I can click on any point here, and it says, okay, add this composition. So mole fraction ethanol of 0.191. The bubble temperature is 83.59. Bubble temperature is basically the temperature at which you first get that first bubble of vapor. So this point right here. So you're going liquid, 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 liquid. And as soon as you hit this point, okay, now I suddenly have a little bit of vapor. The dew point is the opposite. So you have vapor, 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 vapor. And then I hit the vapor line and oh, now I suddenly have the first drop of dew or of water or of liquid. So bubble temperature is 83.59. Y is 0.627. So if you just drew a straight line across at this temperature, you can see that the vapor at the bubble point is around 0.627 and is enriched in ethanol relative liquid, normal distillation behavior. And you can see that there's an azeotrope here. Water and ethanol typically have an azeotrope around 0.894 in the raw tabulated values as well. So again, you can actually make a lot of these using Claude itself. Okay, I'm literally at the end of time, so I'm going to end here. Thank you.